Okay, so in this video, we will look at the idea of solving a linear system, if possible, using the inverse of the coefficient matrix. So we've seen before that given any linear system, it can be rewritten in the following matrix equation as A times x equals B, where if you remember, A is the matrix of coefficients, x is the column matrix of variables, and B is the column matrix of the constant terms. Now, let's assume for a second that the matrix of coefficients A is square and that it is also invertible. So, A inverse exists. If you remember, the property of A inverse is that it cancels A via multiplication. So, A times A inverse equals I, but also A inverse times A equals I. Well, let's see if we already have found A inverse, can we use it to solve the linear system now in the form AX equals B? The answer is yes, and it's surprisingly simple. So we start with the system in the form AX equals B. Okay, well both sides are equal, so we can multiply both sides on the left by A inverse, right? If AX equals B, then A inverse times the left-hand side, which is AX, will equal A inverse times the right-hand side, which is B. Because AX equals B, so you can just replace AX here by B, and this gives you A inverse times B. Well, now, multiplication is associative, right? So we're doing A times X first, then times A inverse, but we can do first A inverse times A, and then multiply X on the left by associativity of multiplication. But A inverse times A, this is simply I, so we get I times X equals A inverse B. But if you remember, the matrix I is the identity matrix, and it has a very special property. I times anything is just the matrix back. This matrix behaves like the real number 1. And so I times x is x. Therefore, our vector of variables, the vector we are trying to solve for, as we know the matrix of coefficients, and we know the matrix of constant terms, and we're trying to solve for x, well, you can see quite simply, the vector of variables x is A inverse times B. And that's it. So whenever you have a linear system where the matrix of coefficients is square and invertible, there is a unique solution to the vector of variables x, and the unique solution is therefore A inverse times B. That's it. Let's do an example, and we'll just keep the calculation simple, so we'll use an example where A is a 2 by 2 invertible matrix. Okay, so here's the system. 9x plus 5y equals 19. 2x plus 3y equals 4. Now before we solve this system using this trick, we'll solve the system using row reduction, and then we'll solve it using this new method and see that they are more or less equivalent. Okay, now here we have several options, right? We could multiply by 1 over 9, we can multiply here by 1/2 and then swap the rows, but we can be sneaky, we can do row 1 minus 4 times row 2, as 4 times 2 is 8. So 9 minus 4 times 8 times 2 is 8. 9 minus 8 is 1. This is our leading one. 5 minus 4 times 3 is minus 12, negative 7. 9 minus 4 times 4 is 16, which is positive 3. We're going to kill the 2, row 2, minus 2, row 1. 2 minus 2 is 0. 3 minus 2 times negative 7 is plus 14, positive 17. 4 minus 2 times 3, negative 6, negative 2. Well, we'll get our second leading one by multiplying row 2 by 1 over 17. And you can see as both x and y are leading variables, the system will have a unique solution. And now we can solve using backwards substitution. So we'll solve for y first. Using its leading one, y is negative 2 over 17. And x is equal to 3 plus, here is a negative 7y, send it to the right-hand side of the equality. So positive 7 times y, but we know what y is, negative 2 over 17. Let's simplify. So 3 minus 14 over 17, common denominator, 3 times 17 is 51. (51) minus 14, subtract 10, you get 41, minus 4, you get 37. So now we have our unique solution. The linear system has, as its unique solution, x is 37 over 17, and y being negative 2 over 17. Okay, let's now solve the linear system using the idea of the inverse of the matrix of coefficients. The vector variable should be A inverse times B. So let's rewrite the linear system, and then we'll solve the system using this method. Let me rewrite the system quickly. So 9x plus 5y equals 19. 2x plus 3y equals 4. The first step is to rewrite the system in matrix form. So A, the matrix of coefficients, 9, 5, 2, 3. X, the vector of variables, x, y, equals B, the vector of constants, 19, 4. This is A. This is uppercase X. And this is uppercase B. We have just shown before that this variable x will be A inverse times B. We already have B, well, we need to find A inverse. As we have a 2 by 2 matrix, you can use the shortcut formula. So 1 over AD minus BC, so 9 times 3, 27, minus 2 times 5, 10, 27 minus 10 is 17. Times, and now we interchange these two entries, and we negate the other two entries. And we leave the 1 over 17 up front as a constant multiple. So just 1 over 17. And now we have A inverse, so we're good to go. our vector variables, x, y, equals A inverse times B, 1 over 17. Oop, I forgot to negate the 5 here. Right, we swap these entries and we negate these 2. So A inverse times B, 19, 4. Leave the 1 over 17 up front as a scalar multiple and multiply these 2 first, and then bring the 1 over 17 inside. 3 times 19, 30 plus 27 is 57. Minus 5 times 4 minus 20. Then negative 2 times 19. Well, negative 2 times 10 is 20. 2 times 9 is 18, so that's negative 38. Plus 4 times 9, 36. Which gives us 1 over 17 times 37, negative 2. And now you can multiply each entry by 1 over 17. So 37 over 17, first entry, second entry, negative 2 over 17. And here's our conclusion, right? This column matrix equals this column matrix, but matrices are equal if they have the same corresponding entries. So the first entry of our left matrix is x, must equal the first entry of the right-hand matrix, which is 37 over 17. And the second entry, which is y, must equal the second entry here, which is negative 2 over 17. And this is exactly the answer that we have obtained when we solved the system previously using for reduction. And so you see, once you have the inverse of the matrix of coefficients, solving for the system is just one line. Multiply the column of constant terms by A inverse, and you will get the vector of variables. And that's it.